So in this section, we want to take a look at sets. Sets are possibly one of the most fundamental and basic ideas or concepts in all of mathematics. We have listed here some frequently used sets. We have the natural numbers, we have the integers, we have the rational numbers, and we have the reals. We generally use a scripted letter, whether it's N, Z, Q, or R respectively, for these specific sets of numbers. A very important definition is something called the cardinality, or the size of a set, which is the number of unique elements in the set. And I notate the cardinality with the set name, whether it's set A, B, whatever I'm calling it, with these two vertical bars around it. So for an example, if I let set A be the set 1, 2, 3, then the cardinality of set A is simply 3. There are 3 unique elements in this set. If I let set B, for instance, be the set 1, 2, 2, 3, 4, in this case, the cardinality of set B is 4. There are 4 unique elements in this set. Yes, the element number 2 is repeated, but when I'm interested in the cardinality, it is simply the number of unique elements in this set. Now, an important set that we encounter sometimes is the empty set or the null set. That is the set with no elements. The notation that I use is simply this 0 with a slash through it, or I can just simply draw the set braces with no elements in it. An example of the null set, for instance, might be the set of all x's such that x squared plus 1 equals 0, where x is a real number. So if I take a look at this, if I try to find all real numbers such that x squared plus 1 equals 0, if we know a little bit about algebra, we know that there is no real number squared plus 1 to equal 0. So this set simply doesn't have anything in it. So we say it is the empty set. And so I can write it either as these curly braces with nothing in it, or the 0 with a slash through it. Let's take a look at equality of sets. I wish to show that the following sets are equal. So I have set A and I have set B. So for set A is the set of all x's such that x squared minus 1 equals 0. So A is the set of all x's such that x squared minus 1 equals 0. Well, let's see what elements are in set A. Using a little bit of algebra, if x squared minus 1 equals 0, then I know that the elements in that set are either negative 1 or 1. 1 squared minus 1 is 0. Negative 1 squared minus 1 is also 0. So this is simply another way that I can write up set A. Set B is the set negative 1, 1. Notice, since these two sets have the exact same elements, we would simply say that set A equals set B. A is a subset of B, and I use this subset notation. I read this as A is a subset of B. If for every x in A, then x is also in B. And so as a picture, everything in A is also in B. So it's almost as if set B contains all of the elements that are in set A. So let's take a look at this next example right here. I'm given set A, and I wish to show that A is a subset of the integers. So set A is the set negative 1, 1. Those are the two elements that satisfy the requirements to be in set 1. And Z is the set of integers. So that is this set, -2, -1, 0, 1, 2, etc. The positive and negative whole numbers. And so I would simply notice that since -1 is an integer and 1 is also an integer, so every element in A is also in Z, we can say that A is a subset of Z. Now let's show that Z is a subset of Q. So let X be an element of Z. So pick any integer in set Z. Then I can write X as X over 1, which is some A over B. I could write any integer and divide it by 1, and it's still the same thing. And so, X then is also an element of Q, or the rationals. So therefore, I can say that set Z is a subset of set Q. Another way that I would simply say this is that every integer is also a rational number, because I can write every integer as a ratio of two whole numbers. It's simply just divided by 1. Let's do this next example. I wish to show that Q is not a subset of Z. So to show this, I must find at least one element in Q that is not in Z. Okay? So let P and Q be integers, okay, such that X equals P over Q with P less than Q. Then X is in Q because it is a ratio of two integers. But since P is less than Q, if I have a fraction, if I have a rational number where the top is smaller than the bottom, where the numerator is smaller than the denominator, then I'm not going to get a whole number. I'm not going to get an integer out. So X is in Q, but X is not in Z. So Q is not a subset of Z, or I would simply say in words, the rationals are not a subset of the integers. There's a definition of a proper subset. A set A is a proper subset of B if A is a subset of B, but A is not equal to B. Okay? So another way to say that is if A is a subset of B, but there's at least one element in B that's not in A, and I use this notation, A is a proper subset of B. An example, okay, the integers are a proper subset of the rationals. The power set. The set of all subsets of a set A, denoted by power set of A, is as follows. It is the set of all subsets of a given set. So let's say I take a look at the set A, which is simply the letters A, B, and C. The cardinality of set A is 3, and I wish to determine the power set of set A. So the power set of set A is the set of all subsets. So I could have the empty set. I could have the set A, the set B, the set C. Notice all of these are sets with only one element. I could have subsets that include two elements, so A and B, B and C, or A and C. And also, every set is a subset of itself, so I could have the entire set of A, B, C. And so I want to count how many how many sets are in the power set of A. So I have the empty set. I have 3 sets with 1 element. I have 3 subsets with 2 elements. And then I have 1 subset with 3 elements for a total of 8. So I simply want to state that there are 8 subsets that can be constructed from this set A. Now, very important theorem, a set with cardinality n has 2 to the n subsets. So what was the cardinality of this set? Well, the cardinality was 3. And so 2 to the 3rd power is 8. And what we've done is we've simply listed those 8 subsets. We now have the definition of the union of 2 sets. The union of 2 sets, read A union B, is the set of all elements that are in A or B. There's a picture or a Venn diagram. Pretty much if you're in the union, you're in A or B, or you might be in both. The intersection of 2 sets is defined as all of the elements that are in A and all of the elements that are in B. That's this middle overlapping section right here. The difference of sets A and B is defined by all of the elements in A and that are not in B. So here's a Venn diagram picture of the difference of A and B. In essence, I take the entire set A and then I exclude any elements that are also in B. So let's do a quick example. Determine the following sets. So set A is 1, 2, 3, set B is 2, 3, 4. A union B would be the set 1, 2, 3, 4. Those are the elements that are in A or B. The intersection, what elements are both in A and B? That would be 2 and 3. A minus B, or the difference between A and B. So in essence, start with set A and then take out the elements that are also in B. That is simply a 1. What about B minus A? Well, B minus A, start with B, take out the elements that are in A, and I'm simply left with a 4. Okay, now let's combine these previous 2 and see if I can't find the union and the intersection. So let's take A minus B, that's this set right here. So 1 union B minus A is the set with just 4. And so 1 or 4 is simply the set with 1 or 4 in it. Now, if I wish to find the intersection of these 2, so 1 intersected with 4, well, let's ask this question. What elements are common to 1 and 4? Well, this first set, A minus B, only has the element 1 in it. The set B minus A only has the element 4 in it. Notice there is nothing common in the intersection, so we would simply say that the intersection is empty. If the intersection of two sets is empty, then that leads us to a new definition, and we would say that two sets are disjoint or mutually exclusive if A intersect B is the empty set. So if there's nothing in A that is also in B, then we say that these two sets are mutually exclusive or disjoint because their intersection is empty. The complement of a set is defined to be all of the items that are in a larger universal set that are not in A. So a complement, and sometimes we write a complement as A with this kind of apostrophe symbol. Sometimes we write it as A with a bar over it. Sometimes I write it with a superscript C to denote complement. All of these are the same notation right here for the complement of a set. In essence, the complement of A is everything that is not in A. Now, this leads us to something called De Morgan's laws. De Morgan's laws are very fundamental in set theory. And I can verify each of these by doing a Venn diagram. So this first one right here says A union B complement equals A complement intersect B complement. Or I might say A or B complement equals A complement and B complement. Let's take a look at what this Venn diagram might look like if I were to draw a rough sketch. So here's A, here's B. And so if I wish to draw A union B is all the items that are in A or B, but the complement of that is everything else. That is this right here. And my claim is that's the same thing as A complement and or intersected with B complement. Well, A complement, that's everything that's not in A, and everything that's not in B is also this right here. Similarly, for this second one, I can say A intersect B complement equals A complement union B complement. If I wanted to draw this one, here's A. So A and B complement, that's everything that is not in the intersection. Well, if you remember the intersection is this overlapping region right here. But I want to find the complement of that. So the complement of that is simply everything else. Notice I'm staying away from that middle football looking section, the intersection. That's the same thing as everything that is not in A or not in B. So notice I would shade the exact same set right here, simply omitting the intersection. And so we call these right here De Morgan's laws, which are very useful as we are going to progress through set theory and then later probability. We have the inclusion-exclusion principle. I'm not going to read that to you. I'll let you read that. And then we can take a look at an example. So in this example, a group of students, each student is taking math or computer science, or both. 1/5 of those taking a math course are also taking a computer science course, and 1/8 of those taking a computer science course are also taking a math course. Are more than 1/3 of the students taking a math course? So I'm given a hint to let n denote the number of students taking math and computer science, and then possibly draw a Venn diagram. So if I draw a rough Venn diagram, I have math right here. I'll just call this other set C for computer science. And I'm going to let n denote the number of students taking math and computer science. So this n right here is the intersection. So I'm given a couple of notes right here. I'm told that 1/5 of those taking a math course are also taking a computer science course. So I can say 1/5 M equals C. And also 1/8 of those taking a computer science are also taking a math course. So I can say 1/8 C equals M. So the number that are taking math only is simply 4n. Notice 4n plus n would be 5n. And the number that are taking only computer science would be 7n. Notice n plus 7n would be 8n. So M union C. Okay, so the union of these two would be 4n plus n plus 7n, which equals 12n. Okay? So if I take a look at the proportion of math, that is simply 5n over 12n. That 5n is the 4n plus the n, which reduces down to 5/12. Okay? So 5/12 of the students take math. So since 5/12 is greater than 1/3, I can simply say yes, more than 1/3 are taking a math course. Before we end this section, I do want to go back here and briefly discuss this inclusion-exclusion principle. Because we might return to it periodically throughout the course. So let A, B, and C be sets. Then the cardinality of A or B equals A plus B minus A and B. So for two sets, what might this Venn diagram look like? So I have set A, I have set B. And so what this is saying is the union A or B equals the number of items in A plus the number of items in B. And if I notice in this Venn diagram right here, I've double counted or I've overlapped the intersection. I shaded it twice. And so that's why I have to subtract out the number of items or the cardinality of the intersection A and B. That's this segment right here, this overlapping region. If I looked at it for 3 sets, the Venn diagram grows. So if I have 3 sets, they could intersect as follows. So set A, set B, and set C. And so what this is trying to say right here is A union B union C, so that's A or B or C, equals the number in A plus the number in B plus the number in C. But then I have to subtract out the pairwise disjoint of each of the 2 sets. So then I subtract out the intersection of A and B, subtract out the intersection of A and C, subtract out the intersection of B and C, and then lastly I add in this A and B and C. This is this triple intersection right here, the items that are in A and B and C. So we call this the inclusion-exclusion principle. Okay? I can use it for 2 sets, which is very common. Occasionally we might use it for 3 sets. So I just wanted to bring that to your attention as we progress through unit number 1.